Shall I start, ma'am?
Yes, you can start.
Okay, thank you, ma'am. A very warm and pleasant evening to one and all present here. We welcome you all to our fourth session of 6-day online ATAL FDP, that is Machine Learning in HPC Environment Best Practices. I, Mrs. Radhika Pasgare, on behalf of Information Technology Department at AC Patil College of Engineering, Kharghar, welcomes Dr. Ujjwala Bangale ma'am to the ATAL FDP on next-gen computing, advances in HPC and quantum technologies for data-driven insights. Without further delay, allow me to introduce Dr. Ujjwala Bangale ma'am. She is a research fellow at London South Bank University, UK, specializing in high performance computing. She has earned her PhD from IIT Bombay in 2018, focusing on knowledge discovery from Earth observation data and multi-core systems. With 16 plus years of academic and 2 years of industrial experience, her research interest includes big data analytics, biomedical imaging, and database technologies. Dr. Ujjwala has numerous publications in esteemed journals and conferences. Today, we look forward to her insights and expertise. We welcome you, ma'am. Please accept our virtual token of respect.
Thank you, Radhika, and thanks a lot for this warm welcome and this kind introduction. Thanks a lot.
Now, I request Dr. Ujjwala, ma'am, to start the session. Over to you, ma'am.
Sure. Can you see my screen?
Not yet, ma'am.
Not yet, ma'am.
Not yet.
Yeah, please let me know because I
Yes,
already saw.
yes, yes,
Yeah.
yes.
Okay. So yeah, good evening, everyone. So myself Ujjwala, and I will give you the brief about the high performance computing environments when we'll use it for machine learning, what best practices we should be following. Okay. So first, we'll look at why do we require high performance computing for machine learning. So basically, this high performance computing has come into picture just because of this business competitions. So uh, everything is business driven. The business develops the app to empower their business. Okay, that apps generate a huge amount of data. Okay, so again, the business analyzes that data to look for some insights and then develop some new functionalities or applications in order to, uh, you can say, to fulfill those requirements. Again, it get embedded into the apps. Again, apps generate some more data, so you could see this cycle over there. Okay, so basically HPC is a business driven requirement, just to continuously improve the analytics to sustain and succeed in the competition. Okay, so and then there are a lot of factors, like there is a voluminous data involved into that. Since we I mean almost many of us have experienced the mantra app, which usually we use for purchasing some clothing and all that. So those who are the old users of app, they might have experienced the kind of evolution happen in the app. Earlier it was just flashing the different products with the cost, but then eventually it started providing some other elements, or you can say other garments along with that, matching with some kind of jewelry, matching with the clothing and all that. So and now it's customized one can even try online. Okay, so this is how the business is striving to be in the competition and trying to uh, lead the market basically. And now in order to do these things speedily, what is required? Okay, so you can see in the cycle the speed is located at the center. Okay, the application develops the data, generates the data get analyzed, and everything should happen fast. Okay, so that speed or fast things causes the entire data or entire environment to enable with the high performance computing power. Okay. Again, another reason we could say that the development of IoTs, Internet of Things, where we can connect multiple objects together, multiple peripherals can communicate with each other, can send the data, okay, and then it generates certain kind of analytics which needs to be consumed in certain time frame, otherwise it becomes useless, okay. So again, here what we require is the speed, okay, so the performance, okay, again, since huge amount of data is involved into that, we require the high performance computing power. Not only that, but then if you consider, I mean, earlier the businesses were looking at the higher level of, or you could say the coarser level of granularity, maybe at country level. So from that country, whether I'm getting profit or not. Now the things have changed. It's not only country level. Now it's going digging to state level, not only state, now city. Even, I mean, the regions like Mumbai, they are digging at suburban levels. Okay, so from what area I get the profit on all that other things, what are the interest likings of these peoples and all. So that kind of analysis, I mean, earlier when it was at country level, now it has sub-region level happening. So you can, I mean, this is, I'm just telling to just realize the kind of that data involved in this analysis. Also, again, in order to get accurate results, it has to improve on the quality. So a lot of pre-processing steps comes into picture to uniquely identify or to get some unique insights. Again, as I said, that the cleansing is important task, then to ensure the consistency, to ensure the sufficiency. So a lot of pre-processing is involved into that. So now, since as I said that it's a business driven, again the business has requirement like the descriptive. It looks for the descriptive analytics like what has happened, predictive analytics like what could happen, and then prescriptive analytics like what can be done in order to handle this particular situation. So that kind of prescription. So
The students is the sixth.
someone else started delivering lecture, it seems. Okay, no worries. So let us continue. So here, what I was trying to tell is, so this is, I mean, since the business, I mean, high performance computing is basically now in picture today just because of this business requirement. Okay, and then since business requires it, the researchers or the people like us works and try to get best out of it. Okay, so yeah, again there are, I mean, while doing that we have seen that there are so many other challenges as well which makes us to use the high performance computing power, like variety of data is involved, like we have the textual data, we have the image, audios, videos, lot of variety of data, and we combine it together. So recently in geospatial domain, there is one model which is taking the data from the social media like Facebook, Twitter, regarding identifying some kind of disastrous thing, even captures the images, say maybe the flood or earthquake something, even considers the images from the earth observation satellite, and then predicts where what kind of damages are there. So just imagine that variety of data. Okay, it's not only the images, videos, audio, but then textual tweaks as well get considered. So variety of data get considered for processing the data. Again, since you are considering variety of data, it increases the volume. Okay, it's a massive data then. Okay? You have huge, I mean, huge number of tweets. It might be the earth observation data. If you consider, that's really a very big data. Okay, with very high resolution images. Again, the velocity, I mean, the rate of generating the data in social media, we all are aware of that, how speedily the data get generated and communicated across the different social media platform. Okay, and then on top of that, we have to also analyze which is a valuable data, okay, which we need to consider, which we need to ignore. So that kind of processing also comes into picture. On top of that, we are applying models which are too heavy. If we consider the GPT model, it's around 170 billions of parameters. Okay, the BERT model, 170 billions of parameters. Even I'll consider one small model which I usually use for generative AI for the medical data. It has around 50 millions of parameters. So, I mean, there are huge amount of parameters the models we are tuning on for. So can just imagine the complexity. I mean, we are I mean, most of the cases we just end up using the pre-trained model, not even bother of training the model. The reason is we do not have sufficient resources to even train that model. Okay, that's a practical scenario. I understand this, that the models are too computationally expensive, that we do not even have the infrastructure to even run that model. So then we end up using the pre-trained model. Okay. So that's what the scenario is. And then on top of that, we also require the immediate feedback from the end users. Okay. I mean, immediate feedback for the end users, as well as even as researcher, in order to progress or improve our results, we also need immediate feedback. But then, yeah. So these are few reasons why we are considering the high performance computing when we apply the machine learning. Okay, so now what are the enablers for machine learning algorithm? I mean, how we can achieve the high performance. So of course, there is one solution to that is using the parallel computing, the parallel programming, where we usually divide our computation to several subtasks, and then we execute it in parallel. Okay, so there is then subtasks may communicate with each other, or may work together to achieve one, I can say, the root task or a major task. So that's basically the idea for this parallel computation. So what kind of steps are involved into this parallel computation design? Okay, so there are four can say steps. The first one is the partitioning. We have to divide our, depending on what do we partition. I mean, there is another topic I would be covering in detail for this. So for partitioning, either we can divide the computation itself, or we can divide the data into sub part. Okay, so and then we execute that partition data in parallel, or partition task in parallel. Then when we partition the data, and basically the idea is we had to give it to the different nodes or processes to execute it, right? So here the communications comes into picture. This communication is also very time consuming task. Okay, the thing is, it depends on what kind of HPC platform you use. Depending on that, the communication cost varies. Okay, so something we are computing locally on local machine, having multiple cores, of course the communication cost would be less. But then if we are using something like that, the message passing interfaces, or clustering, then, or any of the platform for clustering, then the communication cost would be more, because then we end up sending the data to the different nodes. And again, we will require some kind of specialized hardware, say the InfiniBand, or say the mechanisms like which gives you the you can say the impression as that of DMA, direct memory access. So that these kind of mechanisms should be there in order to improve your performance if you are using a cluster kind of interfaces. Okay. So this is about the communication. Once you finish with your computation, then there is a agglomeration. It's nothing but aggregating the data. Okay, so grouping the task into larger tasks in order to improve the performance, for simplifying your programming. And then mapping, it's like you are asking each of the I mean, assigning a task to the processor, and will tell them to execute it. So as I said, that the first part, the partitioning, is again a a very important task when you are executing the algorithm or whatever, I mean, your model on the HPC platform. Okay, so partitioning also, as I said, that we can do the partitioning by dividing the data which we want to process, or we can even divide our model or whatever the algorithm which consists of multiple tasks. Okay, so we can divide the algorithm into subtasks, and then we can make that uh, algorithm or the subtask runs in parallel. But then to do that, we have to always ensure that there should not be any dependency in such subtasks. Okay, because if there is a dependency, then there is a kind of synchronization we need to do when we are doing a parallel computing. Okay, so that synchronization is just to ensure that again all the processors are reached to a certain step and now they are ready to proceed with the another task where all the results from all different processors will require. Okay, so the task parallelism needs to be handled very carefully, since you are dividing one task into multiple subtasks and then making each one run in parallel. Okay, the data parallelism is like you are dividing a data into subchunk, and then on on that data the same operation. Okay, suppose you have say 10 images of 10,000 by 10,000, and then you would be dividing, you have 10 nodes, and then each node will be having that one image. Then uh, this is what I mean, each node will be processing one image of size 10,000 by 10,000. Okay, so this is, you'll do the data partitioning. Okay, and then but then the thing is, when you do the data partitioning, it is usually assumed that you are running the same operation on that data set. So every image you are performing the same operation. That's what the assumption is usually. So that's a data parallelism. Okay, and then in streaming, it's like you can even do the things in uh, can say pipeline or in stream. Like once the first task is finished, the another can be started, but then two independent tasks can go in parallel. Okay, so that can be done by streaming. So now whatever I am discussing, this is not only limited to one HPC platform. It can be used for many I mean, whatever the platforms we use, maybe the GPUs or the clouds or the clusters. Okay, so yes, again, when we talk about the partitioning, there is a fine-grained parallelism and coarse-grained parallelism. Okay, so now here I'll discuss this fine-grained and coarse-grained with respect to the data parallelism. Okay, so but then of course this concept is also applicable for the task parallelism as well. So fine grain, and again, since I mostly worked on the image data, so I will explain it with respect to the image. And then since for image the pixel is the finest level of granularity, so uh, so fine grain parallelism can be achieved at pixel level. Okay, if we talk in terms of the image data. So what is been done in the fine grain, that the small amount of computation work is done on the different data elements at the same time. Okay, and there might be a low computation to communication ratio. Okay, so not necessarily the fine grain will always give you the better performance in terms of processing. Okay, but then the advantage you will get is there will be always a good load balancing, so you need not have to worry about the load balancing. So since I mean, if I considering it as a GPU, then to each of the GPU I mean thread, whatever threads I'm doing, so each thread is responsible for processing one pixel. So that much balanced it is. Okay, so um, we can say that if the gravity is too fine, then it may be possible that the communication cost would be too high, and then the computation, it's basically, see, since we are saying that we are working on the small computation, so If the computation is complex, then it is sensible to do that. But if it's a simple, then you may not be able to experience a good amount of speed up. Okay. Um, so for yeah, so that is there, that you should require a sufficient complex computations on the data in order to get a better performance on fine grained parallelism. The other end is the coarse grained parallelism, where a large amount of computation work is done among the between the several processors, and then uh, there can be a high computation to communication ratio. That means you can achieve the better performance. So the coarse grain are always a candidate where you can gain maximum performance. Okay, but then the another issue with this coarse grain parallelism is it is harder to load balance. Like I mean, I'm saying that I'm distributing. Okay, I'll give the example of this later when I will just demonstrate the things with the help of some case studies on which I had worked earlier. Okay, so this is one thing we need to consider. Again, memory scaling is another enabler. We can store, I mean, it's obviously a huge amount of a data we need to uh, handle, and then we need, for the sake of processing, it should be there in the RAM. And then if we are using some special devices like GPU, then we need to uh, I mean, consider the scaling. But then, yes, there are other aspects as well which we can handle. As I said, that the streaming can be done when we move the data from host to the device. That means from the CPU to the GPU. Okay, but then always there are some. I mean, the traditional system, if you would see, so those systems are not that capable of handling your data. I mean, the RAM won't be sufficient to store this. Again, we handle these kind of issues by again dividing our data, like one image we can divide into subframes, and then we can keep on processing it. So then if you see, these are the alternatives. But then yeah, so memory scaling is one of the high performance computing enablers, which allows you to gain a speed up or your sequential execution. Okay, then yes, so yeah, actually I should have covered this thing. So there are several HPC platforms we already aware of. Like I mean, these are the typical one which I have listed, like the cluster computing, which consists of multiple systems, but then all the systems usually have the same configuration, same, we may say same platform like operating system, and then yes, so that's basically the different MK operating environments which are there. So could be same. So that's a cluster computing. And then the distributed or heterogeneous, which we can just compare with the clouds, which we can use, and maybe not necessarily that all has the same configuration, all that. But then yeah, that can also be used. Then the specialized devices like graphical processing units and the field programmable gate arrays. So these are some special hardwares which we can even use it for parallel computing. So earlier these devices, even the FPGA and GPU, were not programmable. But then, I mean, it's not only programmable, but there are lot of APIs are available where you have to just, I mean, plug and play kind of things are there. I mean, we people work on PyTorch, TensorFlow, and all that. And then there are ready libraries available. You just say that you want to use, say, .CUDA, and then everything will work on CUDA. That was not the case earlier. I mean, when I started working on the GPUs, there were not even the function was there to perform the morphological operation. Okay, so this is the typical GPU architecture. just trying to demonstrate the computing power of the GPU, because I mean, since I work on the images, image analysis, and then GPU is the best candidate for performing the parallelization in for the image data basically. So GPU architecture, if you see, there are multiple multiprocessors. So these multiprocessors nowadays, if you see the GPU architecture, it is referred as a streaming multiprocessor. Okay, so the streaming multiprocessors are there, which consist of multiple processors. You can see here that processor one till, I mean, depends. So many processors are there in one multiprocessor, and every processor has its own local memory, and then there is a shared memory at multiprocessor level where all the processors can have access to that shared memory. Okay, and then there are some other cache if you had to store some other information like constant and texture, and then there is a global memory. So global memory is accessible across all the multiprocessor. So something, if we have to accessible, I mean, some of the data, if it's to be accessible by all the multiprocessors, then we need to store it obviously in the global memory, because it is the one which has access, where we have the access to all the multiprocessor. Otherwise, the shared memory is the fast one. The speed is too high for this shared memory, so it's better to utilize the shared memory efficiently. Yeah, and if you'll see, the base part of this GPU is there are multiple processors, but then if you'll see, there is only one instruction unit. Okay, so what happens that all the processors works on the same instruction. Okay, so since all the processor listens and follows or execute the same instruction, obviously the data will be vary, and on all the data elements, assume that local memory holds the data which you want to process, for example the pixel. Then for all those pixels the same operation is performed, but that is what is the requirement of any of the image processing algorithms. Or I mean, typically I would be talking on that, but yeah, this is the typical GPU architecture which makes it really very suitable for the image processing tasks, such as, I mean, you take any of the image processing tasks, okay, like convolution or morphology or proximity calculation, anything you take, the operation which we perform on one pixel, same operation we end up performing on all the other pixels. So that's the beauty, and that's why it is the architecture of this GPU is quite compatible with the structure of the image. Okay, the format of the image in which we can handle the image. Okay, so basically this GPU, it performs the single instruction multiple data kind of work, and that's why availing us the data parallelism. And since image processing, it's quite computationally expensive task we perform, on again it takes a lot of time. If the resolution is too high, then GPU is the best candidate to process that those image analytics. Okay, so yeah, now yeah, so what we have seen are the different HPC platforms, or you can say the hardware basically. But now looking at that, we do have the supporting software frameworks to that. For example, CUDA. CUDA is the development environment for the GPU. See, GPU, when I say, I am here explicitly talking about the NVIDIA GPUs. Okay. Intel GPUs are also being used for parallelism, but then yeah, I mean, when I say CUDA, it's a proprietary development environment of NVIDIA GPU. Okay, so yes, so CUDA is the environment we can use for this GPU, and then if there are multiple GPUs involved, then we can even use the Horod. Is one of the uh, kind of environment where it allows to connect among multiple GPUs. So it's not now the cluster of CPUs, but then yes, there are multiple GPUs which we can on which we can work. Okay, so I mean, here I just tried to demonstrate the way you are executing it. Say you have 8 GPUs on 2 different machines, then you can simply say that horror run. Provide the number of processors which you say hyphen NP8, so you have 8 GPUs, and then hyphen H you want this host name one, this first host to you use 4 GPUs, the another host to use 4 GPUs, and this is your program. So you want to perform certain training on 2 hosts, and then each host would be using the 4 nodes. Then yeah, so this is SCUDA is typically for the GPUs, NVIDIA GPUs. But if we are working on the cluster environment, then we have the open MPI available. I mean, so I'm talking about the open sources. Even the CUDA environment is readily available. There is no a cost for the CUDA, but of course there is a cost involved for purchasing the GPUs. Okay, so OpenMPI is the cluster. If we have the cluster or multiple systems, we can always configure the cluster and then OpenMPI on top of it. Okay, maybe we require some kind of network OS like CentOS, and then we will use that OpenMPI on top of it, where we can use multiple nodes to run our job. So for example, MPI run happen in 16. So I say that I run the training with 8 or say 16 uh, CPUs or nodes, depending on the things available with you. Okay. Now, yeah, this is there. But then, I mean, this is the development environment. Like PyTorch is, we know everybody aware of, like those who works on machine learning. We in Python, we know that the PyTorch is widely used machine learning library. TensorFlow is another one. Okay, so in PyTorch, this PyTorch distributed. If we'll search for the DDP, distributed data parallel. This is one package we can use for distributing the data across the multiple nodes. Okay, so this PyTorch distributed is one of the API added recently. You can check it. I mean, it always comes with the sample code how to use that, right? So one can look into the implementation details. The another is a TensorFlow distributed, okay, with the help of tfdistribute.strategy. Okay, so it again same thing. I mean, it's just a change in some library, but then yeah, it allows you uh, to work on the distributed platform, like the clusters. On clusters, we can always distribute it. The task or the module can be trained using multiple nodes. Okay. Now, the another important aspect we must consider. Okay, this is, since I am covering the best practices, so I must talk about the data transfer optimization. Like as I said that the communication, okay, the steps which we had seen earlier for this parallel computing, the communication is nothing but data transmission or the module, I mean, whatever you, I mean, the set of statement which you want to execute. Either it would be the data or it would be the set of statement which you want to execute in parallel, right? So what happens that when we are running it on multiple nodes, of course your master node or maybe your system, I mean your data is residing at one place, but in order to execute the task in parallel, we need to divide the data across multiple nodes. Okay, we need to send the data across multiple nodes. Okay, so the data transfer is involved in, even if you consider the GPU, we have the CPU which act as a host, and on GPU we have to run our program. So we need to move our data from CPU to GPU. So there the data transfer comes into picture. And when we talk about the clusters, there also the data comes into picture, data transfer comes into picture, because we had to divide the data to multiple nodes. Okay, so now I mean, it's very essential to consider the data transfer optimization when we look for the best practices to run the machine learning on HPC platform. Okay, so now I'll be covering this GPU data transfer. So for GPU, it's always better to use the pinned memory transfer. So what do we do in the pinned memory? There's some part of the memory we allot specially for storing the data, and then from that location the data get moved to the GPU. Okay, so that area always hold the data which needs to be moved to the GPU. Okay, from your CPU, say I will call it as a host RAM. So host RAM always has certain amount of area memory region from where the GPU will read the data. Okay, so that's a pinned memory, page locked memory. So for data transfer, if it's a pinned memory, then the data transfer is fast. Otherwise, it takes huge amount of time to transfer it without unpinned. So I will show you the performance of this as well, the pinned transfer and unpinned transfer. Then the another optimization measure you can take while using GPU is you should use the shared memory. As I seen, I mean, while discussing the GPU architecture, we had seen that there are several memory hierarchies like the local memory, shared memory, and global memory. So global memory is quite costly. I mean, time consuming if you compare it with the shared memory. Okay, so shared memory is much faster as compared to the global. So use this shared memory efficiently. Okay, usually for operations like matrix multiplication or convolution, where I mean it's image processing applications basically. So another thing is batch data transfer. So even during, I mean, we create the batches while say running. Anyways, we are using PyTorch and we create a batch, and then so basically what it says here that so when we create a batch, we should, and if we are using the GPU, that we should ensure that I mean, the huge amount of data you should transfer at once rather than sending a small chunk of data at multiple times. Okay, better to transfer the larger chunk at a time. Okay, not the smaller one. So batch data transfer with few sends but large transfer are more better than the small chunk and many transfer. That's how it works. Yeah, again, as I said, that there is a possibility of the streaming as well. The GPU also allows you the streaming, so asynchronous transfers can be performed. Asynchronous transfer in the sense we are uh, transferring the data using one function, and there's another kernel parallelly running, probably using the same data which might have been transferred earlier. So that kind of asynchronous work can also be done. Okay, but of course, I mean, some of the things, if we have to ensure that the things have arrived at place and then start with the task, as I said, we always need to ensure the synchronization whenever we use the parallelism. So yeah, so for the correctness of the result, we have to ensure that we are synchronizing wherever it is required. Yeah, so what we have discussed is some of the optimization things which we could easily follow for the GPU. Even I mean, if you have used the PyTorch, then always there is one option while creating the data loaders, like pinned memory, whether you want to set it or not. So yes, so whenever there is option is there, always try to use a pinned memory. Okay. Now the data transfer optimization for the cluster platform. Okay. So clustering, as I said, that at OpenMPI is used more often. So that is a message passing, OpenMPI message passing interfaces. So here also what things you need to take care, like if we have to transfer I mean the same data to multiple nodes. Okay, same data you need to transfer to the multiple nodes, and then probably the multiple nodes are running different operations on that same data set. Then you must use the broadcasting. Okay, so you must use the MPI underscore bcast. B stands for broadcasting. So you can always transfer with MPI underscore send, but then uh, rather than you sending the data using MPI underscore send, you should always transfer the data using MPI underscore broadcast. Okay, so this is more efficient, more faster as compared to MPI send. The same thing is also applicable when you have to reduce the data. I mean, you have to collect the data from multiple nodes. Okay, so you have that MPI receive call as well, but if there is a need to collect the data from all the processes, better to collect it using the MPI underscore all reduce. Okay, so these are the simple, I mean, calls. Anyway, one or the other, we have to use certain call or function to send and receive the data. So why not to use the one which is more faster, which is more efficient? Okay, so these things we need to take care when we are running the machine learning on this high performance computing platform. Okay, again, if you have to send a small amount of data or small variables with small size or messages with small size to multiple nodes, you better aggregate it in one message. Okay, one package, one load, and then that load you send across the node. Okay, that means, I mean, basically you are here also the same principle. Rather than sending something in small amount, the one which you have sent for GPU, send fewer but larger transfer. Okay, if you have to send 10 variables, don't use 10 different calls to send that data. Okay, 10 variable merge together and say add in array 1 to 10, 0, 1, 2, 3, 4, and give that array a as a sending package, and that's how it should be. Okay, there at the end you can always apply the mechanism to explicitly take out the respective variables and stored in the I mean, you can attach the relevant name you want to give to that particular variable for simplicity. Okay, but yes, always there is a possibility of message aggregation, and it improves the performance a lot. Okay, and then yes, that MPI, as I said, the kind of the fine granularity which we have seen possible at the GPU level, because it works on the concept of threads. Okay, I mean, just imagine threads organized in a matrix format and each one working on each pixel and then manipulating. So that scene is not possible in the MPI environment. Okay, so always something which you would be giving to the each of the node, which has usually the coarser granularity, and then when the granularity comes to coarse, I mean, that level it is difficult to balance the workload, but yeah, I mean, some extent you can still manage the balancing of the workload. I'll just demonstrate it with when I'll discuss the case study. Okay, yeah, so this is very important, data transfer for whatever the platform, HPC platform you're using, whether it's a GPU or MPI, you should ensure that the data transfer is optimized. The another best practice is always use the profiler. Okay, so what is a basically profiler? I mean, you might have used it for any of the program nowadays. The environment obeys the different profilers. So profilers is basically helps you to identify that what the functions. I mean, how much time of the time the functions are taking to execute, or how many times it has been executed, something of that sort. The how much of memory it is occupying, something of that sort. So depending on the profiler, you get that kind of details of your execution. Okay, so this profiler helps to identify the communication bottleneck very easily. You can just looking at the profile, you can take out, oh my, this function is taking a lot of time. What could be the reason? Oh, this particular data transfer is taking time. This particular model is taking time. So model, how I can optimize further. There are several ways of optimizing the models as well, right? And we can, so I mean that's another topic actually, that model optimization. But yes, here what I meant to say, that looking at the profiler, you will get a fair idea that what needs to be um, twisted to improve the performance. Okay, so yes, again, as out of any of the platform, the HPC platform has many built-in profilers, whether it's an MPI or it's a GPU. So for MPI environment, you can always say MPI Prof. If it's a GPU, you can use the NV Prof. Okay, so even the PyTorch or TensorFlow has the profilers. We can create the object of type profiler, and we can run the model using that particular object. So you can see that's just a ReLU. I think it's ReLU function has been executed, and then the CPU time, how much time is taken for the CPU for matrix multiplication, add mm, ReLU for convolution, for memory allocation, yeah, and then how much time is taken from by CUDA, that is the GPU, how many number of times it is been called that particular function. Okay, say 5 times it has been called, ReLU has been invoked 10 times, memory allocation is this much. So you will get these kind of details once you profile the whatever the uh, entire execution. Okay, of course, I mean this I'm just showing you the results. Not, you need to add the, as I said, you need to create the profile object. Okay, you can look at the syntax, how we can do create the profile, and how you can attach it with any model, and then the model description, the profiler will come like this after the execution. Okay, then there are the visual profile. Okay, this is something um, of one of the code which I had used earlier for the GPU NDCI, normalized differential cloud index it was. So now again it's a visual one. I mean you can see here that what were the different calls. So first process is of say NDCI NVPP, that is the function call. Then the memory copy, okay, from host to device and device to host, and then they compute like 100%. You can see theoretically there is 100% utilization of this device or the GPUs for computing this. Okay, but it's just theoretically, because I mean, as I said, practically we need to consider the transfer cost as well. Okay, you could see that, I mean, it's hardly takes 10.47 milliseconds for that, but then uh, you cannot even identify which is a block representing the execution, but whereas easily you can see that the time or the block the the data transfer blocks. Okay, these the ones in golden, these are representing the data transfer blocks. Okay, so this small line, it's nearly invisible, but then the blocks are much bigger in size as compared to the time taken for the execution. I will just show it with the help of the plot as well. Yes, but this is important. This is also one of the best practice to always use the profiler when you use the machine learning. Okay, I mean high performance computing. When you use the high performance computing, then you ensure that you must try to look at the profiler. You can look for the bottleneck and you can try sorting out, and you can work on the specific component. Then okay, this transfer is taking a lot of time, let me optimize the transfer. This function is taking a lot of time, can I just split it? Can I take something which is independent of that and run in parallel too? So there are so many other things that we can think of later. Okay, so yeah, that's about the base practices. And then I would also suggest to use, uh, I mean, this is typically, I mean, I will say it for the image processing, like the image processing operations, like the morphological operations, the convolution operations, the proximity, okay, the histogram computation. I mean, these are some typical operations which we usually use for the data pre-processing, like for example, age detection, segmentation, object detection. If that's objective, then you always end up by segmenting the data first, like, and then doing whatever that other task you want to do on that. So segmentation becomes the important thing. So while segmenting, you may apply the morphological approaches. Okay, you may apply the Gaussian as well, just for sake of smoothing and then looking at the edges. So, or for the noise reduction. Okay, so uh, yeah, this is something Bandra is showing, which is applicable for the remote sensing images. Okay, um, so yes, so these are the transformation. We may rotate, scale, resize. So these are some of the transformations which we perform on the image. And then uh, yes, for all these kind of operations in future extraction, for even the autoencoders and everything, and for, I mean, we know that all these things are, if you have the GPU available with you, the things will work so speedily for you. Okay, otherwise, you'll just end up spending, when your system will spend even 2 days to come up with some kind of results for from a small data. Okay, because image processing anyways it's expensive, and then you try to do a lot of things on that, lot of computationally expensive tasks you want to do, and then yes, it will take its own time. But then you use GPU and hardly in 10 minutes you will get the required result. So that's how, I mean, speed up you will get. And yes, for regardless of the HPC platform, whatever HPC platform we use, uh, it's important to note that unless and until you have a huge amount of data, the HPC, the high performance computing power is useless. Okay, you will not get improvement if you have a very less amount of data to process, and then you are using GPU to process that. In fact, you'll end up taking more time on GPU rather than CPU. So CPU will process it more faster than the GPU. Okay. Again, another restriction, as I said, I mean, I might have said it several times that when you try to even run two strings in parallel, you need to ensure that there is a independence of operations. There should not be any kind of dependency among two different a task which you want to run in parallel. Okay, so that independent task, this word is very much important. If there somehow there's no possibility of performing it independently, better you do it on CPU, because CPU is expert in processing the sequential data faster. There is no one, I mean, other than CPU, there is no other device which can process the sequential operation faster. Okay, so the device which I'm talking is a GPU. GPU is only meant for parallel processing. If you ask a GPU to perform sequential tasks, the performance would be really horrible. I mean, you cannot even compare it with CPU, because that device is not meant for performing that task. Okay, but then parallel, yes, the task can be done in parallel. Then there is no comparison between the time taken by CPU and GPU. Okay. Now, as I said that I would be explaining these things, I mean, whatever I just like the best practices which I have used for at least for transfer and all that. So I will just demonstrate with the help of some example. the case studies. So yeah, I had worked earlier on the oil spill data, where I mean this oil spill, it has huge impact on the coastal and marine life. Okay, it hampers a lot of. I mean, it has. I mean, it affected a lot the coastal habitats, local industry, fishery business. So a lot of impacts because of this oil spill on the sea surface. And then considering the unique characteristics, like it forms certain shapes, and then considering its spectral characteristics as well, we had come up with certain methodology where both the spectral properties and spatial properties of the oil spill images, which are obtained from the Landsat 7 satellite. So those are used, and then the spectral properties, basically we had applied the band ratio algorithms. And for spatial, like it's just a kind of image processing you could think of, like where the connected components are identified from the image, and then the morphological attribute profiling is applied on that images. So the different attribute considers considered here are the physical attribute, like the gray mean and standard deviation, and then the geometric attribute like elongation, solidity, slick complexity, and orientation. And then there is a cascaded filtering of these things, and then these attributes. And then entire methodology is implemented on GPU, and also um, on the MPI platform, and then integrating both MPI and GPU as well. Okay, so let me give you one small example of how much benefit you can get when you can, I mean, when you will perform the transmission and the actual computation. As I said, that the computation, whatever the actual operation we need to execute. Okay, yeah. So this one is, yeah, just a simple code. I mean, because I had done the coding on the CUDA environment, C CUDA. So everyone is aware of the C syntax. So if I had to handle one image, always I will require two for loops to handle the rows and columns. Okay, but here in the CUDA code, can you see any for loop? No, they're just if statement which will simply check for the boundary. I mean, it should not try to access the index out of range and throw the error. So I'm just trying to check over the index should be in the range. Okay, but there is no for loop, and both the functions perform the same task. Okay, so here straightway the complexity of this particular computation, which is in terms of number of rows and columns for the image, it's reducing to certain constant, right? So that kind of computation complexity has been reduced. Now we'll look at the time. Okay, here I mean, rather than the accuracy, we will more focus on the speed if when we talk in terms of performance, because we are using, I mean, focusing on the high performance computing. So let us look at the timeline. So the red line, which you can see, that's a time taken by only GPU. Okay, function execution, that is band ratio computation only by GPU. The green line is showing the function execution, like the computation plus data transfer. Okay, so and then the blue one is only sequential execution on CPU, which takes around 6.88 seconds. And with the GPU, the execution is done in 0.0167 seconds. So if you see the communication time, this communication, like including data transfer, it takes 1.03. Okay, without, I mean, just take computation, it is 0.0167. So communication cost is 64 times more than the computation cost. Are you realizing? Computation is very small, but the communication, the data transfer cost is almost 64 times than the computation. But still, there's a huge data, involved into this. So still we can see the this particular computation on GPU is 6 times faster than the CPU. Okay, still it is 6 times faster than the CPU. But if you don't consider this data transfer cost, it will be around 412 times faster than CPU. Okay, just take 6.88 and 0.0167, so it will be around 412 times faster than GPU. But that's not the case. We cannot eliminate the data transfer, right? It's a mandatory step. We need to move the data from CPU to GPU, right? So this data transfer cost is too huge. So why I was focusing on the data optimization, because HPC are powerful. They will do the execution very fast, but this data transfer is really very uh, you can say costly in terms of I mean, speed performance. If we talk in terms of performance, the data transfer is too costly. Okay, but still the data size is bigger, and if I keep on increasing, if multiple images comes into picture, of course I'm going to gain a lot of speed over CPU. Yes, but then you need to always consider that yes, there is not only computation, there is a communication cost involved when we use the high performance computing platform. Okay, so this band ratio, I mean, whatever the results you have seen, that is with the data transfer. Otherwise the it would have gone somewhere, I mean, more than 6 seconds. Okay, so um, so band ratio, sorry. Okay, so optimized data transfer, I'm just trying to show the difference of with the pinned memory transfer and unpinned memory. Okay, if we consider the data size of say 18,432 by 18,432 for using unpinned memory, it takes around 1,000 milliseconds, and with the pinned memory it's hardly 247. Okay, so there is a huge transfer cost we are saving if we use a pinned memory transfer. Okay, so always ensure that whenever you are using PyTorch or TensorFlow or any of the libraries for this I mean Python or any other environment, always there will be option for pinned memory. Okay, the syntax may vary depending on platform to platform, but then always there will be option of pinned memory, and you just say true or set that particular parameter to make the GPU use the pinned memory transfer. Okay, because it's really you will get a very good performance, more speed if you use pinned memory. A few images actually. I mean, I'm not here focusing more on the results from that perspective, but of course from the computation perspective I'll focus. Like as I said, when I developed that time, there were no even standard CUDA routine for the morphological operations. Okay, but then yeah, here also, I mean, so this is what I had coded that time. So the computational complexity in terms of rows and columns multiplied by the size of the structuring element, whereas on GPU it's just a structural, I mean, it depends only on the size of structuring element. That to be, we are convolving, I mean, we are moving first horizontally and then vertically, so more optimization further. So morphological basic operations, it's around 220 times faster than the CPU. Okay, if you see by varying the size, of course it doesn't depend on the size of the image. Okay, what it depends on is only the structuring element size. So as the structuring element size increases, the size of the sorry, the time taken by the CPU increases, but then GPU it remains somewhat constant, doesn't depend much on, because it doesn't depend on the image size. Okay. Okay, so as I said earlier, that I mean, even we can use it for feature extraction. So as I said earlier, that cursor level, I mean, how we can achieve the balancing of the workload. So see, as you see in that methodology, I had extracted the connected component. So assume that there are 100 connected components, and then I have 10 nodes, then each node I divided 10 components. So that level I try to balance the uh, workload for each node. But then there may be possibility that some of the components are too big, having say around 20,000 pixels or more than 90,000 pixels, and then there is one component hardly having 200 pixels. Assume that there is one node which have received all 10 components, which has uh, maximum size of the pixels for each of the if the component is 500, and by chance it has happened that there is one node where every component has size more than 50,000, then it's not a proper, I mean, balancing. But then I cannot help it, I cannot go in that level of granularity, right? I mean, so this is what happens, that here we try to balance the load at our level, but then at the structure of say components, we are not sure what can be. So yeah, the idea here is the truth process dividing the task across multiple nodes to extract the features, like all these features to extract from the each of the connected component. Okay. So now moving further, what kind of parallelism is achieved is there is a root process which had distributed the components to the nodes. So this is second layer is nothing but the MPI layer, and then the third one is a GPU. Okay, so then further each node or each core is further dividing its tasks to the GPUs. Okay, so this is a multi-level parallelism. Okay, so if we have that MPI interface as well, then you can obviously, I mean, here we achieve great speed up. Okay, so by using the multiple HPC platforms like MPI and GPUs, we have achieved around only 11 times speed up. Why only 11? Because I said that there are a lot many sequential tasks which needs to be done by CPUs only. But still, CPUs have been executing. Uh, Again, there are multiple nodes. Okay, with so basically considering, I mean, GPU distributing across multiple nodes and using the GPU which is K40, the execution time taken for these many connected components, around 33,638 components, the time taken uh, for 64 cores is 10 minutes, whereas for 8 cores plus GPU it is 88 minutes. Okay, so yeah, so if it's taking 88 minutes considering all the 8 cores and 40, just think of a single core without GPU, how much time it will take. Yeah. Okay, so yes, so this is about the performance. I won't talk much about the evaluation. Yeah, but then the another case study which we had worked. See, usually, I mean, it's a both like oil spill or earthquake. You take those are some kind of disasters, maybe natural or man-made. But here, these are some tasks where we require immediate responses. So wherever the immediate responses come into picture, we require the high performance computing power because we need to generate the result fast, right? We cannot tolerate. So the methodologies are used for this. I mean, based on the HPC, are the reason is because those are the disaster events, and then you need to generate it as fast as you could. So that's why for both the use cases, I had used the HPC platforms. And then I mean, for earthquake also, since the SIP feature, the scale invariant features are extracted, and then what are the steps involved into this, like convolution kernel, then the difference of Gaussian kernel or the extrema detection. So this is the performance table you can see, the talking about in terms of time, or even you can look at the plot, say for the image sizes of 15,000 by 15,000, the convolution is 57 times faster. The difference of Gaussian kernel is around 15 times faster. The extrema detection is around 35 times faster. So you will definitely get a speed up even if you have a good amount of data. Then yeah, this another task like proximity and then yeah, I mean another plot for proximity and this thing. So it may happen that some of the uh, tasks like say this is a proximity matrix calculation and then minimum value extraction. So proximity you are getting huge speed up. Okay, it's around 586 times faster than the sequential one. But there are some operations where the speed, I mean there won't be much speed up, it remains somewhat constant only. Okay, so because that's the nature of that operation where you cannot just get any speed up, nothing more like extracting the minimum value. Okay, but still faster as compared to the sequential one. Okay. Then another deep learning on the earthquake data. Okay. So yeah, so the TPUs are also used along with this, but then the optimized case where you'll see that CPU plus GPU is uh, uh, is uh, is doing the same task in 16 or almost 17 seconds, whereas the CPU is taking 264. Okay, so yes, so from this, I would like to summarize that HPC is mandatory for applications that requires near real-time responses. As I said, when I had used it because that is something. I mean, those are the disasters. In that case, one should have always certain mean to respond in near real time, right? So whenever such scenario is there, use of HPC is sensible, and that to be you have to use a massive amount of data. Okay, so use of HPC is mandatory. There you cannot, I mean, just avoid it. Okay, but use of HPC platform for machine learning is suitable only if you have massive data set. If you have very small data, then you will not get any benefit out of it. Okay, and so obviously, I mean, if you have the computationally intensive operations, as I said, nowadays the deep learning models, the foundation models, yes, I mean, having around 170 millions or billions of parameters. Okay, so I mean, I don't think if we don't have HPC, we can, I mean, we'll end up taking months and months to train our data on those models. I mean, those models itself are that complex, and then on top of that, we want to run on our massive data. So it will take months and months if there is no GPU. Okay, so that's there. So we have to, I mean, these computationally expensive algorithms nowadays are making us use the high performance computing power. And then as compared to my observation, like cluster is not feasible, I mean, even to manage and maintain, probably very costly affair. But then GPU are quite and cost effective as compared to, okay, I'm saying as compared to, because it's not, even, I mean, if even if I'm not sure exactly how much, but then A100 and A40, those would be costing too high, looking at their uh, architecture, because I think A40 GPU is having around 10,000 CUDA cores. So you can imagine as many number of CUDA cores plus few tensor cores. So that must be very expensive. But yes, it's more reasonable to use and easy to use as compared to cluster environment. And for machine learning, yes, GPU serves our purpose. Okay, GPU really serves our purpose. I mean, because since I haven't worked on this BERT or GPT models on training explicitly on that, but then for textual data also people are using it for people using GPUs for that. Probably the vectors you are, I mean, storing the frequency of the words and all that, arranging in some that, I mean, even for the vectors the GPUs performs really excellent. So vector processing also, because we can mold the threads the way we wish. We can mold it as a vector, as a matrix, depending on your requirement. You can even manipulate your frequency words and all that. So it would be useful to use GPUs for this whenever we have to use these foundation models. So yes, and I've just tried listing the performance gains or the primitive operations I had used earlier. For the proximity computation, it was around 586 times faster. For morphological, it was around 220 times, and for convolution, it is 57 times faster. So, and also important thing, I would say the best practices must involve is the communication optimization. You should always take care of data transfer optimization, and don't forget to profile your execution. So profiler gives you a fair idea that where you can improve on the in order to achieve the more performance. Okay, so yeah, that's it from my end. Thank you. Please feel free if you have any questions.
Uh, Participants, if you have any question, you can ask. Uh,
Or even, I mean,
mm,
you can reach out to me later if no question as of now.
uh, Ma'am, I guess there are no questions from participant side.
Anyone
Can
is
I, ma'am?
having any question, please ask. Radhika ma'am, I think there are no questions.
Yeah, yeah, ma'am.
Okay, fine. So yeah, but then if any question, you can always reach out to me.
Yes, ma'am. Yes, ma'am.
On behalf of everyone here, I extend our deepest gratitude to Dr. Ujwala Bangale, ma'am, for her insightful and engaging presentation. Her expertise in bridging the gap between the power of high performance computing and the transformative potential of machine learning has been truly inspiring. Ma'am, please accept our virtual token of appreciation.
Thank you, madam. Thanks a lot for this appreciation.
Thank you, ma'am, once again. And we would like to acknowledge and express our thanks to all the attendees. Your presence has made this session all the more meaningful and memorable. Thank you all. And we will meet you again at tomorrow's session at 6 p.m. Thank you and have a good day.
And dear
Attend.
participants, for joining.
Yes, ma'am.
Thank you, ma'am.
Participants' attendance and feedback link for both the sessions are given in the chat box. I request all the participants to go through it.
Okay, thanks
Ma'am,
everyone. Thanks
please
for
share
joining.
Uh,
your PPT so that I can share
yeah.
that PPT with the participants.
Sure, sure.
Someone has raised a hand. Sorry.
Okay, fine. If
Okay,
there is
okay.
no
Oh, yeah, ma'am.
question, yeah, then may I leave now?
Mhm. Yeah,
Yes,
yeah, ma'am.
ma'am.
Yeah, yeah.
Okay, thank you. Thanks.
Thank you. Thank
Thanks,
you so
ma'am.
much.